Okay, let's start. So I'll go through this material slightly fast today because I have already gone through this material once some time back. So we will discuss the concept of process and what we mean by an interrupt. How do processes repeatedly, the process that is getting executed on the CPU repeatedly changes after short intervals of time in modern computers. There are many reasons, several, I mean, 3-4 reasons for which a context, this type of change of an executing process is called a context switch. There are 3 or 4 reasons or mechanisms by which a context switch can happen, and we will have a look at them. A process basically is a program in execution which has been loaded into memory, or at least pages or relevant to the, not all pages probably of the entire program binary, but the relevant pages have been loaded into memory and are currently either ready for execution or they are currently executing on the CPU. A CPU typically executes only one executable at a time, and the process is characterized by its program counter, that is the instruction of the next instruction that is supposed to get executed, the stack, and the data section. The data section means the portion of the memory where data is stored, and stack is kind of the temporary portion of memory which keeps on growing and shrinking. We have seen this diagram several times in this entire course, and you will keep on seeing this diagram in your next course also, in your operating systems course. Here is, this is the kind of an logical description of the virtual memory space of a process. What is a virtual memory? We have discussed in the last class. It starts from 0 and it goes up to a maximum value. The maximum virtual address space value depends on the number of address bits, and also there might be further restrictions. There are several portions. The lower addresses typically are reserved for the text segment of the program. The text segment is basically the collection of instructions. Then you have the data segment, the portion that holds the global variables and statically declared data. Then you have the heap, which is the portion from which you dynamically allocate memory. And at the top is the stack. A stack is useful when you have to temporarily store some information. For example, when you are going for a procedure call and there is a possibility that your register contents have to be saved before you jump to a procedure. All of these we have in the entire semester, in this entire course, we have discussed in detail. Typically, the heap grows upwards in the address space, and typically the stack grows downwards in the address space. The virtual address space gives an impression. Again, I am repeating the same thing that I taught in the last class. The virtual address space gives an impression that as if every program has this virtual address space available to it, okay, on the computer. However, that is quite impossible, because as you can guess, if one program is occupying the entire address space, how can another program occupy the same address space? In general, simultaneously, we have all modern computers are time shared systems in which there are multiple processes running at the same time. How is that possible? Well, it is possible because you, at any given point of time, the application programmer feels that he has the entire address space available to it, a contiguous address space starting from 0 up to a maximum value available to it. This is not the physical reality, because this, first of all, allocating so much of contiguous memory space, even if the max value does not span the entire available address space, even if the max value is limited to something, okay, so much of contiguous address space allocation in main memory is quite difficult. Okay, so typically the main memory allocation happens by virtual address to physical address translation, and then allocating the necessary pages into memory. These pages follow a fully associative placement scheme where any page or a chunk of uh, memory content, it can be either text or it can be data or anything, that can come from your non-volatile memory, which is typically hard disk, and it can come into main memory as and when required. From that it goes to the cache, etc. However, in this chapter we are not considering cache. We have considered cache is an on-chip resource, and basically if you want to understand virtual memory, it is most of the times it is sufficient if you consider the interaction between main memory and cache. Of course, there is this concept of TLB, which we studied in the last class, which makes this address translation faster. Now, this is a very, very important diagram, and this diagram, even in the next course, you will be asked to kind of memorize, because this is one of the most common questions in Viva, the interviews, is that describe the process state diagram and draw it and explain it. A process state diagram, initially a process is in a new state, then it is admitted in a ready queue. These queues, ready queue, etc. Later on we will find something called IO queues. These are data structures which will be maintained by the operating system. Okay. A process is new means it has been relevant pages of it have been loaded into memory. Then it is admitted to the ready queue means it is ready to run when it is given the opportunity. However, if currently another process is running on the microprocessor, that process is in the running state. And so this process, which is at the front of the ready queue, remember is a collection of processes, just like any other queue. Okay, that must wait till it is given the opportunity. Now the running process can be interrupted. Interrupted means the CPU by electrical means, it can receive a signal at particular pins telling the CPU that you must stop doing whatever you are doing currently. And the CPU receives these interrupts, analyzes it at the beginning of execution of every this interrupt mechanism is checking this interrupt. These are called interrupt lines of a CPU. These are dedicated pins on the CPU chip. This checking of the pin status and analyzing what caused the interrupt. Because there are other information also provided to the CPU along with the same. Gives the CPU hint of what interrupts can also be. For example, exceptions can be generated. An exception is an internally generated hardware interrupt. For example, the opcode is not valid. There was a divide by 0, etc. Okay. Anyways, either internally generated exceptions or external interrupts can come to the CPU. At the before committing to the execution of an instruction, the CPU checks its interrupt request lines or certain dedicated pins. And if an interrupt is detected, the CPU first saves the current state of the currently executing process at particular locations of memory. And then, depending on the cause of the interrupt, then it consults a particular table, an array of addresses. Okay, where this we will come to it. There is particularly it basically jumps to a particular location which can take care of handling that type of interrupt. When an interrupt happened, the current process typically is evicted from the CPU. Who will evict the current process? This is a very important question. Is evicted means what? It is evicted means its state is saved into memory. You cannot just suddenly say that I will forget whatever the process was doing. Up to whatever job, whatever is its state, up to whatever work it has performed, that is saved into memory. And then another operating system module to handle that type of interrupt comes in. Okay. One of these operating system modules might be something called a scheduler. The scheduler gives certain amount of time to every process to run. When that time quantum or time slice expires, the scheduler mechanism is invoked via an interrupt process, which then decides what to do with which job to next decide. I mean, which job should run next. Of course, this scheduling mechanism is it runs in a kernel mode, and it has the privileges to make modifications to the program counter as and when it wants. I mean, program counter modification through jump instructions can also be indirectly performed. But basically, it changes the program counter and makes the CPU jump to the address of the next process that is supposed to run. Please understand that this address need not be the beginning address of the next process, because the next process that is supposed to run probably is an unfinished process. When a process is interrupted, it is sent back to the back of the ready queue. Okay. So currently something which is at the front of the ready queue, extreme front, should run. However, depending on situations, if there are emergency situations and some high priority process has come in and some VIP process has come in and is probably not at the front of the ready queue, but it must be given the opportunity to run immediately, the scheduler in such cases can select that process and give it an out of turn opportunity to run on the CPU. However, this is usually rare. Usually the process which is at the front of the queue gets the opportunity to run. How much so? Continuously this kind of a thing keeps on happening. Okay. There is a process, say P0 running, then there is an interrupt, or it can be a system call. A system call is a call made by the program to the operating system requesting certain services. For example, it wants to display something on the monitor. This is a simple service for which the operating system must help it. A normal user process with normal user process privileges, in the user mode, you cannot write to the memory locations or to which your monitor or display monitor is mapped. Okay. So this type of requests are made. The operating system then it saves the state into process control block. A process control block is a data structure which stores the current state of the process. Typically, a process control block contains several pieces of information. For example, the state of the process, the number of the process. Any process in Unix has a number. Okay. The program counter, the registers, etc., the memory limits, the list of open files, etc., etc. In any, if you will find, you can find the process control block data structure, the C structure corresponding to a PCB, say in Linux. If you just search on internet, you will find details of it. Even in textbooks, this is given. So the save is state into the PCB, then it is decided that process P1 will run. So this is a very simple mechanism where there are only two processes. There are only P0 and P1, that's it. But usually there will be much more number of processes. Then P1 is given the opportunity to run. Again, P1 executes for some time. Again, it is interrupted, and again the CPUs saves the state into the process control block, jumps to a kernel routine which can handle that type of interrupt, and that again maybe it is the scheduler. However, scheduling is not the, I mean, this end of time slice is not the only reason for which processes can be interrupted. There are other reasons also, as we will see. There are certain, you will notice that in this diagram, there are certain portions of the time where neither process P0 nor process P1 is running. And this is pure overhead. Okay. The change from an executing process from process P0 to process P1 back to process again P0, etc. Any change is called a context switch. So this context switch takes certain amount of time, and that is pure overhead, that is not useful to the user as such. However, we kind of accept it because of all the other advantages that context switch gives us, that on one single CPU, you can run multiple processes on a time shared basis. Okay, all modern operating systems are time shared. Now, this how does this time slice expiry business happens? If suppose the scheduler decides that I am going to give the next process about 10 milliseconds to run. After that, there must be a context switch. So the context switch time is typically kept much, it is arranged such that it is usually much smaller than the time quantum. Because like say if 10 millisecond average time on average is given to one process, context switch will probably take 1 millisecond or less, much less than 10, like less than 10% of this. Okay, so suppose the scheduler decides it is going to give process P0 10 millisecond to run. Now it basically initializes a counter with a value which at the given clock rate of the counter, it's a hardware counter. Okay, it is initialized to a value which at the given clock rate would count down from a starting value to 0 in exactly 10 milliseconds. Okay, so suppose it is something like say 1 gigahertz. 1 gigahertz is 10 to the power 9. There are 10 to the power 9 clock cycles in 1 second. 10 millisecond is 1 by 100 of that. Okay, so it will initialize it to a value of 10 to the power 7 or so that in exactly 10 millisecond, it will count down to 0. This down counter, when it reaches 0, it raises a 0 detection signal, and that is kind of an interrupt to the processor. Okay, so it can send an interrupt to the processor saying that this time slice is over, or this process is over. Okay, so you must do a context switch. Okay, we have noticed that there is fundamental lack or gap of understanding among students when you ask that who interrupts the CPU. When the time slice of a process is over, who will interrupt the CPU to tell the CPU that time slice is over? Many students answer the operating system interrupts the CPU. Are operating system, how will it interrupt the CPU? Operating system is just another piece of software which sometimes on a time shared basis it occupies the CPU and runs there. Several different modules of the operating system. Ultimately, the operating system is controlling your computer. That is fine, but it is not a magic godlike software that it does not need any CPU to run. It's not like that. So when you say that the operating system interrupts the CPU, where is the operating? How will it interrupt the CPU? It is not currently executing. Currently, your process is executing, say, and that has to be interrupted. So the operating system plays an indirect role. The operating system scheduler arranges such that the execution of a process will be interrupted through this timer mechanism. This type of interrupts are called timer interrupts. But the operating system cannot directly control the interrupt. It cannot directly cause any context switch. The timer interrupt mechanism is hardware controlled. Okay, any interrupt mechanism is primarily hardware controlled. Okay, so you should understand that. Fine. Corresponding to every I/O device, slow I/O devices like say magnetic tapes, which have become obsolete nowadays, disks, terminals, etc. There are, because multiple processors might be wanting to do operations with these units, there are job queues attached with them. Okay. First of all, there is a ready queue which shows which processes are currently under contention. They are in ready state, and if given the opportunity, they can run. As usual, it is a queue typically it's a linked list implementation maintained by the operating system. This linked list are linked list where each node is the process control block structure. Okay. They are at the queue header. There can be heads and tails pointers directly. The head pointer is obvious, but the tail pointer also gives you direct access to the end of the queue if you maintain. Now, magnetic tapes maybe there, maybe not be there. Otherwise, say magnetic disk hard drives, the ones that we have studied, they are very slow devices. Okay. One of the components of the delay was the queuing delay. Now, this is the reason why this queuing delay happens, because currently this PCB3, the process control block for process number 3 probably is currently in contention to occupy the to do its transaction with the hard disk drive next. What about the other process number 14 and 6, which are waiting? They don't know how much time process number 3 will take. So that part of the queuing, that part of the delay is kind of non-deterministic. Okay. If process number 14 and process number 6 are unlucky, process number 3 will take up a lot of time occupying the magnetic hard disk drive, and then their delay would be adversely affected, because typically the devices cannot handle multiple processes at the same time. Okay, so they will process only one at a time. Similarly, there might be multiple processes wanting to display stuff on your monitor. Okay, but they have to wait, because currently the monitor is displaying something which had been written to certain memory locations from which its controller reads and displays on it. Okay, so currently some other process had done it. However, say process number 5 also wants to display something, it must wait in its proper queue. Okay, so relatively simple concept, but this shows why suddenly this queuing delay component of a hard disk type IO device happens, and this type of queues might be maintained for many other processes also. If this had not been in order, there would have been chaos. Let me give you an example. Suppose there is a printer, okay, in a large department, and this printer is being used by several faculty and several students, each of whom have account and access to this printer. All of them are firing their runs to the printer at the same time, asynchronously. Nobody has any coordination with the other. What will the printer do? Suppose the faculty is printing a 20-page paper. It will finish first that job, then it will go to the next job in the queue, then it will go to the next job in the queue, etc., etc. Otherwise, if it had tried to give shared access, this is a situation where queuing is necessary. Okay, ordering is necessary. Otherwise, if it had given access to first the teacher, then after some time the student, then again back to the faculty, then maybe to a staff, then maybe to another student, what would have happened? Can you imagine what would happen at the printing? Everybody's work would get mixed up basically, right? So you will get one page of the one paper, then another page of another paper, maybe something else like that. It doesn't make any sense. So that it doesn't work. These IO devices typically work in strict coordinated fashion in a first in, first out type of operation. Okay, typically, and they maintain a queue structure. So the question is, so this how can a process that is there in the ready queue and then it is selected for execution by the scheduler mechanism get holds of the CPU, and then it is evicted. How it gets hold of the CPU, I will come. It is still not clear. How does the scheduler suddenly give access to that process that has been selected? I will come to it. But first, let us consider other possible ways by which a process can be evicted from the CPU. There can be an IO request in the process. For example, there can be a scanf function in the process, or there can be a printf function in the process. That printf and scanf function, how much time will it take to complete is not clear. Printf function is not clear because on your monitor there is a queue. corresponding to your terminal, there is a queue. So the process might need to wait. So whenever, and its scanf function obviously depends on human interaction. So when it is going to happen, nobody knows. So the operating system does not waste time by keeping this type of, these are called like processes which are waiting for IO to keep occupying the CPU. It kind of sends out, evicts that process when automatically when an IO request happens, and sends it to an IO corresponding IO queue. When the IO operation has been done, the IO device, it kind of sends a signal to the proper hardware units. Okay, maybe again to the certain registers can be set, etc. So after some time, the operating system might check these registers to check or certain memory locations. These registers typically will be memory mapped. So these are not like physical registers sitting there. These are memory mapped registers, virtual registers. So they can read that, and when it finds that the work is done, it again makes that process go to the back of the ready queue, so that when its turn comes, it can execute. Time slice expired, we have already discussed. Time slice expired is not a fault of the process. There was no IO operation, still it is forced to be evicted, so it goes and keeps standing at the back of the ready queue. The third procedure is forking a child. What is forking a child? Forking a child is there is a process by which an process itself might give rise to another process, and that is, I will not go into the details of that mechanism. You will learn it in great detail in your operating system theory and lab courses next semester. This is a very important mechanism, happens all the time. For example, when you type usually you type an a.out on a Linux command prompt and press an enter. Typically that will be executed as a new process, as a child process of the shell process that corresponding to your command line terminal. Okay. So usually after forking that child, the parent waits till the child has finished. That is the typical mechanism. Most of the times the parent will wait. There are mechanisms by which you do not want the parent to wait for it, and you will get back your command prompt directly and keep on typing their new commands. With your child process will keep executing in the background. That is the mechanism on Unix by which you can do it by typing and say /a.out ampersand and press an enter. That ampersand shows that you want the process to run in the background. Okay, so that can happen, but typically the parent will wait for the child process. Until the child process finishes, you will not get back your Linux command prompt. So that is the example of the shell process corresponding to your command prompt waiting for the child process to finish. And finally, when the child has finished execution, that parent process again comes back and goes to the back of the ready queue and again waits. See, everything this when we are saying it is waiting, finally after some time it gets a chance, you might be surprised that it doesn't seem like that, because you instantaneously get a response from the computer whenever you want as a user. But that's not the case actually. Okay, what do you mean by instantaneous? It is instantaneous at human time scales. Okay, human beings cannot react to events, or they cannot distinguish between events when at a time resolution of less than 1/10th second. So when it is less than 0.1 second or so, our sense of distinction of two events, like if one event has happened in 0.05 second and another event has happened at 0.09 second, it will seem to us that they are happening at the same time almost. So our time resolution is limited to kind of a scale of 1/10 second. Okay, 0.1 second or 10 to the power minus 1 second. That is our human time resolution. That too is quite fast, but okay, say 0.1 second. What about the computers, modern computers? They are working at gigahertz speeds. Okay, they are working at, you are giving a time slice of 10 millisecond to a process to complete. 10 millisecond is 0.01 second. So it is 10 times faster than your fastest response time. So there is no way you will feel any issues regarding this context switch. To you, for example, I am opening this Microsoft Teams and PowerPoint and giving a lecture. It seems to me that all the time the only process which this currently this computer is executing is my process. I can shift this mouse and it is kind of shifting the cursor. Okay, so these are kind of interrupt events happening, or I am making probably a system call to the operating system to let me give this process the permission so that the display can is like this. This cursor shifting on the display can happen. Okay, but things are happening so fast. There is no delay between my shifting of the cursor and the actual shift of the cursor on the screen. There is a time gap. Okay, these are not instantaneous events, but the time difference between these two events is so small that physically I cannot distinguish between them anymore. Modern computers take advantage of this feature to give you an impression that you are performing continuous execution of only one process at a time. That is not the case. On Linux, you can type the top command to see how many processes, several processes are running on your system. On Windows, you can type Alt Control Del and then click on Task Manager to see how many processes are running on your system. You will find tens of processes, at least 20-30 processes are running on your system. Even if they are not all your application processes, many of them will be daemon processes. Daemon processes are processes which keep on running in the background without disturbing the user or without even the user knowing about them, but they are very important. For example, the networking daemon process, which handles all your incoming and outgoing connections, etc., which keeps listening for any incoming connection from other servers, etc. Okay, so of course several processes are running. They are getting slices of the timeshare repeatedly. Okay, that's this how much slice would a process get is controllable by the operating system. When the process will get access to the CPU is controllable by the operating system. Okay, whether a process will at all get access to the CPU or it will be ignored, although it is there in the ready queue, it will be ignored. That can be controlled by the operating system. This is an extreme case. And one important thing, these gray boxes, IO request, time slice expired, then in IO queue, fork a child, wait for an interrupt. When these events happen, the process goes to a wait state. When the process goes to a wait state, the process is not even under current consideration to execute. Please understand the difference between a process in Redis queue and the process which have undergone this type of events like an IO request or expiry of time slice. Expiry of time slice is different. The process immediately goes to the ready queue, but the others, the process goes to a wait state where it is currently not even under consideration to execute. Only the processes which are in the ready queue, they are under active consideration to be executed. This is the difference between processes in wait state and ready queue. Both of them are in memory. but the process which is in the ready queue has very low current priority of getting executed. It is not even under, I mean, there is zero consideration of it getting executed. Okay. So currently, say like our vaccination mechanism, okay, the priority is initially it was people above 60, senior citizens. Then it was above 45. Then it became adults to 45. Now maybe in near future it will cover the children, etc. But currently till children are covered or kids under 12 are covered, their kids under 12 now are very low. They are almost, there is no priority of them currently getting vaccinated until vaccination for the other groups have reached a certain level. So this is a very important concept and you should understand this. Now scheduler, won't go into scheduling because scheduling is a huge topic that will take weeks of discussion when you probably take your operating system course. Long-term and short-term schedulers. Primarily short-term scheduler is what people are concerned with, which allocates what process should run and how much time quantum should it be given. Okay, there are two types of processes. One are IO bound process, which spends more time doing IO than computations. And there are some CPU bound processes, spends more time doing computations, but very long CPU bursts. Okay, so typically the type of soft like this power, like say an word processing software, like say MS Word or LibreOffice or presentation software. These are IO bound. When like this type of software become processes and execute, these are mostly IO bound. The computations they do are not that complicated, and even if they are complicated, they are done at extremely slow speed because the CPU, the human response is very slow. But they take, because everything depends on the human response, they are IO bound. Okay, and Microsoft Word document depends on its content, which is typed by a human being usually, which means it is continuously, it is depending on what the human, how the human being is interacting with it. So this is an IO bound process. Whereas if you are running a computational software which is performing a long computation, that's a CPU bound process. Not too much. Initially you take some inputs from the user maybe, but after that it is completely CPU bound. Fine. So let us now come to the concept of interrupts. There are several types of IO devices which you already know. There is an incredible variety of IO devices supported by modern computers. They usually they are accessed through something called ports. Okay, the ports are either kind of connected in series, and finally they share something called a bus, which is this is called a daisy chaining or shared direct access. Bus is a very common feature in any modern computer. It is a shared resource where different IO devices can plug in. There is a well-defined bus protocol which these IO devices understand and they play according to the rules. Usually only one IO device can read or write data, or write data at least only one at a time on the bus. When it is done, another IO device takes over, etc. Okay, there can be complicated bus protocols, okay, which require complicated controllers. Some of them are called host adapters, which are completely separate circuit board containing the bus controller hardware. These host adapters can be plugged into your CPUs in particular slots. Now there are two ways to control devices. Okay, There can be dedicated instructions or direct IO instructions. Okay, they work. They are designed to interact only with IO hardware. We have not studied that type of instructions in MIPS, but they can be part of your instruction set architecture. These IO instructions directly interact with particular IO devices, but the more common feature is to treat these IO devices uniformly and perform something called memory mapped IO. In memory mapped IO, the IO devices are provided space in memory through which they can communicate with the CPU. Okay, they can read and write data onto that location, and the CPU can read and write data from that location. Now, typical PC bus structure, say a PCI bus, is a very common bus, shared bus on modern PCs. Nowadays, PCI Express and all these fast buses have come in, which are kind of improvements over them. There can be other buses also. For example, there can be expansion buses through which keyboards and other serial and parallel devices, for example, mouse, etc., they can be connected. And there can also be other buses to handle data storage devices like the iSCSI bus. The iSCSI is such a complicated protocol that the iSCSI protocol itself needs another controller, and it gives rise to another internal bus on which multiple disks might be attached. The most important feature of this diagram is look at how multiple resources are sharing the same bus. Okay, any node in this graph can connect with any other node through the bus. The only issue is that the bus cannot handle multiple electrical signals at the same time. Okay, so that has to be respected. That restriction has to be respected. Okay. The processor can interact with devices like, say, monitor via the memory. So actually, through any IO device through a memory mapped process. So the processor reads and writes data onto the memory, particular locations, and then the device goes and collects that data from the memory. The only issue with that problem is that scheme, I mean, that kind of an arrangement is that now this processor to memory, this path becomes very, very busy, right? Because now many devices are fighting to get access to memory to perform read and write to their portion of the address, because they will collect this data from there. If there are many IO devices like that, then there is a fight for this memory common resource. Okay. Also, this diagram is slightly confusing because this shows the cache to be outside the processor. That is not the case in most modern processors. The cache is actually in chip. So earlier, maybe there were faster memory modules which were off chip caches, but nowadays by cache we mean something, as we have studied, it is inside the processor chip. Okay. To avoid this problem of multiple processes fighting for this memory, and another problem is that when processes are directly accessing memory, when processes are many processes are accessing memory and performing reads and writes, when the processor itself might need to wait to perform regular memory accesses. Okay. Suppose there is a page fault, or not page fault, say something has to be written to memory or has to be fetched from memory. Processor does not have any access, means the processor cache does not have any access. The processor is currently handling many other requests. Okay, so this problem can happen, but still it is accepted. To free the processor from the burden of handling every transaction on behalf of every other devices, IO devices, something called direct memory access, or DMA, has become very popular. What is DMA? Suppose you want some device wants to interact directly with memory. Okay, some IO device. You do not want to involve the processor at all. There is something called a DMA controller. The processor tells it that okay, you handle this transaction, this is the starting address of the data, this much by many bytes of data have to be written or read. When you are done, tell me. In the meantime, let me work on other things. So it goes off and works on other things. The the DMA controller, there is another additional piece of electronic circuitry called a DMA controller, which handles access to this memory module but from other IO devices. That DMA controller performs the transaction. When the transaction is complete, it informs the processor, maybe through an interrupt mechanism, that the transaction is done. Okay, so the processor can come back and resume that process when the time comes. Okay, so this device IO port locations are typically these instructions which deal with these devices directly. They usually small numbers. Now, question is why? What is the other advantage of this interrupt mechanism? If you did not have an interrupt mechanism, you repeatedly need to poll, check the IO devices in series repeatedly, asking, do you need my service? Do you need my service? But that is a very wasteful. Like I gave an example that where a doctor, instead of sitting in his chamber and waiting for the patients to come to him if needed, the doctor himself every morning goes to every house and asks, do you need my service? Is anybody sick? That's a very wasteful resource, because most of the time in a house there won't be anybody sick and the doctor's service won't be required. It will help more if the doctor remains in his chamber and when his service is necessary, somebody comes to his chamber. Okay, the process of interrupt is exactly like this. Instead of polling, it only involves the CPU when needed. Okay, either processors or other devices. Some interrupts are called maskable, which means they can be delayed a little bit, but some are non-maskable. Typically, the exceptions, like these dangerous errors, like so this is an Intel Pentium processor. What is a vector number? I will come to it. But look at this, the vector number, the smaller vector numbers. Okay, divide error. Okay, bound range exception, invalid opcode. These are device not available. These are dangerous errors. Okay, these are like hardware errors. So these type of things are non-maskable typically. Okay, divide by zero error cannot be masked. It has to be immediately handled. When a CPU, before executing every instruction, it looks at its interrupts at these interrupt request lines, which are pins, electrical pins. If it finds an interrupt, it first saves the state and then it transfers control to an interrupt handler. Okay. Where to go to the interrupt handler? Interrupt handler is a small module in the operating system, a small piece of code which is specialized in handling that type of interrupt. How does the CPU know where to go to handle it? Well, it is given some hint. Along with the interrupt, some codes, typically numerical codes, are also provided to the CPU, which tells the CPU you go to that particular location where you will find that proper interrupt handler. The CPU first goes to something called an interrupt vector table, which is an array of addresses. The vector number is the index of the array. Using the small number that had been provided to the CPU, it indexes into a particular location. In, for example, if it had a say a page fault, okay, it will be provided as a hint the number 14, and it will use this index to, it knows where the interrupt vector table is. So there might be some register which will store the starting address of this table. This is a very important piece of information. It goes to index number 14, and this entry is the address of the operating system routine or the interrupt handler corresponding to a page fault. It will then jump to there, and that routine will do its job, handle the page fault, then again give back control to the operating system by setting the program counter value, and again to another process by setting the program counter value to whatever location is needed. this thing repeatedly keeps on happening every clock cycle. Okay. The CPU waits for an interrupt. If it detects an interrupt, it does something. But it happens so fast that we do not feel that our work is getting disturbed. Okay. So there's some more. So this concept of DMA has been explained here. Have a look at it. So any questions, students, about today's concept? Anything you want me to further clarify? So these portions are being taught from the operating system book by Galvin. You will find the PDF on internet, and also you can buy this because anyways next semester this will be your textbook. Okay, so looks like there are no further questions. So if you have questions, send me emails. But otherwise, in terms of classroom teaching, this is my last lecture with you this semester. From next week, pipelining, the topic of pipelining will start. And your exam, the third exam, will be on 15th November. I will send an email detailing. 15th November is Monday. During the class slot, as usual, it will start at 12 and it will go up to maybe 1:45 or so, like you had the second exam. Similarly, and the details of the portions, etc., everything, what would be the syllabus, everything we will mention by detailed email. I just wanted to give an advance intimation that your third exam for the theory will be on 15th November. Okay, thank you. I hope you have enjoyed this course till now, and again you will also enjoy the other portion that is left that will be taught by Professor Bhargav Bhattacharya. Many concepts of this course will be useful in the operating system course that will come up next semester. That's why this course is a prerequisite for another operating system course next semester. Thank you very much.
Thank you.
Thank you.